Good evening, everyone. I welcome you all to today's live session for the course Elements of Mechanical Vibration NOC25-ae17. This is the week 12 live session for this course, and we have already completed 11 live sessions up till now, and this is the last live session for this 12-week course. So today's live session is about what has been covered in this week's lecture, which is about continuous system. So up till now, how we started the course was we first worked upon modeling of a system, of a continuous system as a single degree of freedom system. Then we talked about how to deal with that kind of a system, how to find out the frequencies, how to find out the natural frequencies, how to find out that how the system is going to respond upon application of some external force, which can be impact loading, which could be sinusoidal force, which could be a continuous or periodic force, everything of that sort. Now, as we discussed, as we have discussed earlier also, that that was for a single degree of freedom system, right? Okay, I should first add a slide over here. So essentially what we were doing was if we have a rod, something like this, then we were modeling it as a single degree of freedom system. However, we talked upon about degrees of freedom, right? Where we got to know that the degrees of freedom are essentially dependent upon how many number of mass points we have multiplied by how many number of free movement the system is having, right? Like for a mass which is in the three-dimensional space, something like this, x, y, and z, if there is a mass here like this, how many degrees of freedom does it have? Okay, so it is going to have a 3 degree of freedom system, correct? This ball is going to have a 3 degrees of freedom. And when we write its equation, it will be a 3 degree of freedom system, correct? But when we talk upon about that, if the same ideologies apply to this cantilever beam, so upon when we talk about container mechanics, we say that there are infinite mass points in this beam, and hence there are infinite degrees of freedom, correct? Which means there is going to be infinite number of natural frequencies because it's a continuous system. So there's going to be infinite number of natural frequencies. But then it becomes a complex system, right? It becomes a complex system because now my movement is not only changing with time, but it is also changing with the distance from the fixed end. Correct? And that is why in order to find out this equation of motion, we need to do what? We need to use the concept of partial differential equations, right? Now, if you look that I have the freedom to model it as a single degree of freedom system, right? Something like this. I can do it because it's a mathematical model. But is it accurate? No, it is not. Though if we say that the movement is very small and it is in the linear range, then we can do it. Okay. But this is not an accurate model of the system, especially for the cases where we want precision and where we want to avoid even any kind of a failure, even a very small failure also. Okay. There we cannot model it as a single degree of freedom system. So what we can do is we can model it as a n degree of freedom system, as an n degree of freedom system, which is going to have n omega n's, n natural frequencies. Okay. But then again, this is not exactly portraying us how the system is behaving, right? It is not exactly portraying us how the system is behaving. So the option left with us is that we model it as a continuous system itself. Okay. Okay, we basically model it as a continuous system. Now, in case of continuous system, what happens is that we consider every single part of this beam and we write an equation which will be a partial differential equation, right? And it will depend upon time, it will depend upon x. So we say that, let us say the movement W is going to be what? Is going to be a function of x and t, where x is the distance from this end. So this is the way we should be modeling it. But then again, it depends upon how and where the application is all about. It may happen that sometimes, even for a n degree of freedom system, we only need to model for a specific kind of degree of freedom. Why? Because you know that for a system, if there are n degrees of freedom and a certain kind of actuation is given such that it is close to the mode of any, let us say, ith mode, modal frequency, then it is going to oscillate with that ith mode only. So only that mode is going to show the dominant effect. Other modes are not going to show us the effect, or the contribution will be very minimal as compared to the ith mode, right? So we just need to model the system for that ith mode and we are going to get the solution. But then this is a case where we know that only this is the possibility that can happen with the physical system. But in physical cases, that is not always true because we want our system to be multitasking, right? I want it to actuate at a constant rate. I want to actuate it as a sinusoidal behavior. I want some random motion. In that case, I need to take up all the possible cases that can happen in the system. And for that, we need to model it as a continuous system. Now, I'm not saying that the continuous modeling of the continuous system is necessary. It may happen that the n parts that we are dividing it into, it is going to give us a, it can give us an accurate solution, right? Or at least the approximate solution, because then we don't have to go into the continuous system. Okay, so it all depends upon what practical application we are into, what kind of safety we want to take with our system, right? And yeah, how complex is our system? That also matters, because if the system is very complex, then modeling it as a continuous system, it will be very difficult, right? So this is the case. However, it all looks good when we talk about single degree of freedom, n degree of freedom, or even continuous system when our system is linear. When we get into the nonlinear system, even the 1 degree of freedom system is nonlinear. We can't even get the closed form solution for the 1 degree of freedom system, right? So when we are talking about a nonlinear system, things become more complex, and then the choice how we should model our system becomes different. However, here we will learn about how to solve the questions which will be related to the continuous system, because definitely if a system is working in the linear range, then we can definitely use the basic concepts of partial differential equations in order to find out the solution. Okay, so coming on to question number 1, just a second. Okay, so the question is, determine the natural frequencies and mode shapes for a free rod. Firstly, what is a free rod? There's a rod. That's it. It's a free rod. It is not constrained from any of the end. So we need to find out the natural frequencies of this rod. Now, in order to find out its natural frequency, we are definitely modeling it as a continuous system. Okay, sorry. So since the ends are free, right? The ends are what? Free. So at the ends, the stress is going to be what? The stress is going to be zero, and also the deflection is going to be zero, right? So at the ends, okay. So at the ends, the unit strain is 0, right? Which means what? Del u by del x is equal to 0 at x is equals to 0 and x is equals to L, right? Why del u by del x? Because del u by del x is actually the deflection u with respect to the x, with respect to the change of x, because x is in this direction and the deflection is in the lateral direction. Okay. Now, if you remember that in the theory part you must have learned, or in the book also you can find it, that u can be written as u, which is a function of, as I told you, since it's a continuous system, the deflection u is going to depend on x as well as time, right? It is changing with x and it is changing with time as well. So this can be given as capital U of x into g of t. So the solution u is a product of solution u, capital U of x, which is a function of x, and then g of t, which is a function of time. Okay. So u of x is what? A sine of omega c by x plus b cos of omega x by c. Okay. So u is a sinusoidal kind of a function which is dependent only on x. And then we have g, which is a function of time, given as c sine of omega t plus d cos of omega t. Okay, so if we combine this, we get u of x. Now, since at the boundaries we have the differential of u with respect to x as equal to 0, so first we need to find out the differential of u with respect to x, which is going to be what? Which is a definitely partial differential equation, because u is dependent upon two variables x and t. So we are using partial differential of u with respect to x. And when we do that, we consider the second variable as a constant. Okay. So del u by del x is going to be what? It is going to be a omega by c. Differentiation of sine is cos omega x by c minus b omega by c sine omega x by c into c into sine of omega t plus d into cos of omega t. This is the differentiation, partial differentiation. Now we need to find out what? We need to find out that what are the values of the differentials at x is equals to 0 and x is equals to L, and equate it equal to 0. So firstly, del u by del x at x is equals to 0. What is this going to be? A omega by c, sine part is going to be 0, into c sine of omega t plus d cos of omega t. This will be equal to 0. Clear? This is what we get. Now, for this to be equal to 0, what are the possible cases? So firstly, either C and D both are 0. So if C and D both are 0, it means that with time, U is not changing. Okay, which is not true, because we are assuming that there is some kind of a vibration that is happening in the system, right? So C and D cannot be equal to 0. So definitely A is going to be equal to 0. This is the first part that we are having, right? The second one, which is del U by del X at X is equals to L is equal to 0, which implies we have now X is equals to L. Look over here. We have to put L over here, right? L over here. So it will be A omega by C cos of omega L by C minus A omega by C sine of omega L by C into C sine of omega t plus D cos of omega t is equal to what? 0. Okay. Now okay, wait. Here it should be B. Now A we have already assumed is equal to 0. So this goes to 0. Now for these terms to be equal to 0, what are the probable ways? C. Again C and D cannot be equal to 0. And if we take B also equal to 0, then what is going to happen? Since B is multiplied with C and D, if B is equal to 0, then again there is no kind of a vibration, right? It says that either there is no deformation or there is equal deformation, which is not possible. Okay. So B cannot be equal to 0. So which means that sine omega L by C is equal to 0. So B cannot be equal to 0. So sine omega L by C is equal to what? It is equal to 0. It is equal to 0. Now, from this equation only we are going to get what? The natural frequency equation, right? Because since sine omega L by C is equal to 0, what is going to happen further? Omega n L by C will be equal to what? When are the sine function equal to 0? We know that the graph of sine is something like this. It is 0. No, this is the cos. Yeah, pi to pi. So the sine function, sine of, let us say z, and this is z. So the sine function is 0 at 0, pi, 2 pi till n pi's, where n can be infinity, because it's a repetitive kind of a behavior. So if omega n LC is equals to n pi, then it satisfies our equation wherein n can be pi, 2 pi, 3 pi, dot 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 till n pi. You can write n pi where n can tends to infinity. Let us just skip it because we have already used n till n pi. Okay. Now if omega n LC is equals to n pi, then omega n is going to be what? N pi C by L, or n pi by L, and C is what? Under root of E by rho. Under root of E by rho. Rho is the density, and then E is what? Young's modulus. So frequency Fn can be written as omega n divided by 2 pi n by 2L under root of E by rho. This is the expression for the frequency in hertz, and this is the expression for the frequency in radians per second. Okay, so these are the expressions for the frequencies. Now, this is what the frequency is all about. If these are the frequencies, then how can we write the solution? How can we write the solution? So the solution can be written as U is equals to U naught cos of n pi by L into x into sine of n pi by L under root of E by rho into T. This is going to be the solution for the free vibration of the system for Any of the natural frequencies you can have. Now the natural frequencies can be for n, 1, 2, 3 likewise. Okay. So what is going to happen in that case? The system is going to show, a sinusoidal behavior with change of mode shapes that we'll be discussing further. Okay. So yes, this is the solution, and the question asked, the question was telling to determine the natural frequencies. So this is the expression for the natural frequency. Sorry. Coming on to question number 2. Here we are supposed to find out the natural frequency of a bar with one end fixed and a mass attached at free end as shown below. Okay. So in the previous question, what were we doing? In the previous question, we had a free bar. Both ends of the bar were free. In this case, firstly, one end is fixed. One end of the bar is what? It is fixed. And the second end is free, but then there is a mass m that is there on the free end. Okay, I hope that the question is understandable. So we are supposed to find out the natural frequency. Now, if you look into this question clearly, for this kind of a question wherein we have to find out the natural frequency for a cantilever beam, it has already been done, I guess, in the book, or it is discussed in the class as well. Just a second. Yeah. So we have firstly a bar like this, which has row A and E, right? This is the first case. After that, we have a mass over here at the free end. Okay, at the distance of L, and this is just fine. Okay. Now we need to find out the natural frequencies. So how are we going to deal with this problem? First thing is clear that we need to model it as a continuous system. If we are modeling it as a continuous system, then we are going to get a partial differential equation, and then we'll be using those partial differential equation to find out the natural frequencies. So firstly, coming upon what is the equation, right? What is the equation for a cantilever beam of or a bar of one end fixed and the other end free? If you remember that its equation is given like c square, second differential of u with respect to x equal to second differential of u with respect to time. Where c was what? Under root of e by rho. This was the expression. If you need to find out the solution, how are we going to get? U, which is a function of x comma t, is again given as the multiplication of u as a function of x into t as a function of time. Again, how we assumed in the previous question. So this we have as, sorry, a cos of omega x by c plus b sine of omega x by c into c cos of omega t plus d sine of omega t. Okay, this is going to be the expression. Now, this is the expression. We have the boundary conditions, right? The boundary condition says that at the fixed end, Okay, at the fixed end, the deflection is going to be what? It is going to be 0, correct? Now, if at 0 comma t is equal to 0, if we'll put it into this equation, what are we going to get? Again, if you look closely, we'll put x as 0. So the second term, which is c cos omega t plus d sin omega t, it is going to be like that only. We'll get just a multiplication of a into that term, and then we have to make it equal to 0. So what is it going to give us? It is going to give us as a is equals to 0. This is what we are going to get. So we know now that, okay, a is equal to 0. Other than that, there is one more interesting thing, which says that there is going to be a balance of a force at the end where a mass is given, right? So at that time, whatever the force or pressure or tension that is acting in the bar, what will it be equal to? It will be equal to the inertia force of the mass, capital M, correct? By force balance. So what is it going to give us? It is going to give us A into E into del U by del X, where this is a function of L comma T, will be equal to. Why here we have taken L and not X? Because this balance of inertia force is going to happen only at the end of the bar, right? Because mass is there only. This is equal to what? Minus of M del square U by del T square, where U is a function of L comma T. Again, over here we have L because this inertia force is going to act at the end of the bar. Okay. So if we put the expression of U in this equation, what are we going to get? Putting the expression of U in the inertia in the inertia equation, what are we going to get? So we are going to get that AE omega by C cos of omega LC into C cos of omega t plus d sine of omega t m omega square sine of omega L by C into C cos of omega t into d sine of omega t. This is what we are going to get as an expression, correct? Now, C cos omega t plus d sine omega t is the present there on both sides. So we can just cut it out like that. Or what we can do is bring the right hand side towards the left hand side, take it common, and then see that, okay, this total term should be equal to 0. Now, C cos omega t plus d sine omega t cannot be equal to 0. So definitely A e omega by C cos omega L by C minus m omega square sine omega L by C is going to be equal to 0, right? So it is then going to give us A e omega by C cos of omega L by C is equal to m omega square sine of omega L by C, right? Now, if you look closely over here, one omega will get cancelled with another omega, and this cos and sine we can take it over there, so it will go give us tan of omega L by C, right? So m omega tan omega L by C is going to be equal to AE by C, right? AE by C. Now you know what is C? C was nothing but under root of E by rho, right? So if we wanted to convert it in that form, something like that, so we can do it. Then it will be something like omega L by C, tan of omega L by C is equals to AE by C into M. Now over here, what we have done is we have basically multiplied with L by C. So there also we are supposed to multiply with L by C. So this will be C square. So we can essentially write this as alpha into tan of alpha is going to be what? Equal to beta, where AEL by C square into M. Okay. Now we can write C as what? Under root of E by rho. EE will get cancelled and there will be a rho in the above. So beta can be further written as A rho L by M. And if you look closely, rho was what? Rho was the density of the bar, right? Rho was the density of the bar over here. So I'll write over here also. Rho is what? Density of the bar. Area is A is cross-sectional area of the bar. Okay. And L is what? Is the length of the bar. L is the length of the bar. So A, your density into cross-sectional area into length is going to give us what? It is going to give us the mass of the bar. Correct. It is going to give us the mass of the bar. So this is going to give us where M is the small m is the mass of the bar. Okay. I hope this is clear, right? So this is what we are going to get as an equation. Now this is a transcendental equation, right? This is a transcendental equation, which means that we have to solve it for alpha, which is going to give us the value of omega. But then our alpha is present inside the tan alpha thing, right? It is present inside the tan alpha as well. So we need to solve it simultaneously. So it's basically a transcendental equation, okay? So this is the expression that we get. Now, since we want to find out that what is the expression of the natural frequency, how we can do it is we can use that transcendental equation and then consider the assumption of linearity in order to get the expression for the natural frequency. Now, how are we considering, will we be considering the linearity? So we have C as under root of E by rho, right? Which can also be written as what? E A L by M under root. So if we consider that this mass M is very small, okay, the mass M is very small, this will tend to what? Infinity. This will tend to infinity. Now, if C is going to infinity, C is going to infinity, then alpha, which is omega L by C, is going to be what? It will tend to 0. Correct? Because in the denominator there is C. Now C is going to infinity for a very small value of M. Then alpha, which has omega L by C, since C is going to infinity, this omega L by C is going to 0. Okay, it will tend to 0. Now, if it is tending to 0, what we can assume is, we can assume that alpha is very small. If alpha is very small, then what do we know? Tan alpha is nearly equal to alpha. So from that expression, we get alpha square is equal to beta. This implies omega L by C square is equal to beta, right? Omega L by C square is going to be what? Beta. So omega 1 is going to be nothing but C by L into beta to the power 1 by 2. C by L into beta to the power 1 by 2. Okay. So this is going to give us C by L into under root of rho A L by capital of M. Because this was the expression of the beta that we got over here. This one or this one. Okay. Okay. So this was what we got. Now this can be further written as what? This can be further written as what? If we convert C again in terms of E and rho, we are going to get it as under root of E A by M L. E A by capital M into L, which is going to give us G by delta S to the power 1 by 2. Okay, where delta S is nothing but MGL by EA. MGL by EA. Do you remember what is MGL by EA? MGL by EA was actually the static deflection when in the first or second live session only, I think we did this question where we had a bar and there was a mass capital M suspended at the bar, and then considering that the bar is having a negligible mass as compared to the capital M, we were supposed to find out the static deflection, right? And then we assumed it as a spring mass system where we assumed the stiffness as EA by L, and then we found out that okay, since Kx is equals to mg, x was mg by EA by into L, right? So the same expression we got over here. So using this, we can write omega 1 as g by delta static to the power 1 by 2. Okay, I hope this is clear. Now, coming on to question number 3. I hope that you understand that what are the difference that we are seeing over here in these questions that we are solving over here, other than what we solved for a single degree of freedom or for a uh, 2 degree of freedom system, or for that case, even the multi-degree of freedom system. We are basically using over here a continuous system, and then we are modeling it using a partial differential equation, and then we were using those partial differential equation and the boundary conditions in order to get an expression which could be used for finding out the natural frequency. And for the first case, we got the expression. For the second case, we got the expression in terms of some transcendental form, and we assumed some kind of a linearity, or we assumed that the deflection of the mass is very small. In that case, we use this assumption to find out the natural frequency. Okay, I hope that is clear. Now, determine the equation for the natural frequencies of a uniform rod in torsional oscillation with one end fixed and the other end free. Anyways, in the previous question, I would like to uh, give, uh, give this certain comparison that do you remember for a spring mass system? we had omega as under root of k by m, right? What did we do here? We assumed m to be very small, which means that we considered it as a bar of negligible mass and then a mass of capital M, correct? So this was basically a case of a single degree of freedom system where we modeled it as a single degree of freedom system, and then we found out the expression, right? So if you relate it, if I use this and k is EA by L, so we get omega as under root of k, which is EA by L into M, right? This is what we got for that expression, for that question that we did in, I guess, live session 1 or 2, right? This is something related to that. You can see over here that the expression is also the same. When we considered the small m to be very small, we get the same expression as we got it from here. So that is why I was saying that even when our system is continuous, what we can do is we can model it as a single degree of freedom system, but then it depends upon the application. Like for here, we considered that a small m is very small as compared to others. So if this is very small, then this is the expression that we got. So we didn't have to, solve the partial differential equation or use the partial differential equation, apply the boundary conditions, then get the transcendental equation, then assume. It was not needed. We could have just assumed it as a single degree of freedom system where the bar was having negligible mass and then there was a mass capital M which we were using in order to get the natural frequency, that we could have got it from that assumption only. Okay, so that is why it is essential that we know how we model the system depending upon what application and what are the prospects that for which our physical system is going to be used. I hope this is clear. Coming on to question number 3. We have to determine the equation for the natural frequency of a uniform rod and torsional oscillation with one end free and the fixed and the other end free. Okay, so basically what we have is something like this. Okay, now this is a uniform rod and we have to consider the torsional oscillation, something like this, the torsional oscillation. Okay, now for this kind of a bar, the first question is what is going to be the solution. So again, see, the solution is again going to be of the same form as we assumed for the previous 2 questions. I'm not getting into finding out the partial differential equation and everything because this is already done in the book. We are supposed to solve some questions over here. So I'll just write the expression for theta, which is going to be nothing but A sine of omega under root rho by g into x plus b cos omega under root rho by g into x into again what? C sine of omega t plus d cos of omega t. Okay, this is the expression for what? Theta. Now, first thing, at x is equals to 0, what do we have? At x is equals to 0, the deflection is going to be 0. The rotation is going to be 0, right? So we have v is equals to 0. And at x is equals to L, what do we have? We have the torque equal to 0. The torque should be equal to 0, no? Because this is a free end. Okay, there's no forcing that is happening over here. So this is what the case is. Now, if we use these, we are going to get again a is equal to 0. Obviously, because we have theta is equals to 0, so definitely a is going to be what? Equal to 0. Correct? Now, coming on to the second boundary condition, which is for torque is equal to 0. So for that, then again we are going to get cos of omega into rho by g L is going to be equal to what? 0. This is going to be what? Equal to 0. Okay, L will not be over here, no? It will be in the multiplication. Both the boundary conditions are going to give us this expression. Now, if we use this expression, see again, we have the cos of something equal to 0. When we look into the cos graph, how is it? Cos of 0 is what? 1. Like this, right? This is what? Pi by 2. This is pi. This is again 2 pi. This is 0. This is cos of z, and this is z. Okay? So this is how the curve goes. So we know that the cos function is going to be equal to 0 at what? Pi by 2, 3 pi by 2, then we'll have 5 pi by 2. So the odd multiples of what? Pi by 2. So how can we write the odd multiples of pi by 2? As n plus 1. Okay. So if we write that omega into under root of rho by g into L. Omega we can write as n, natural frequency. It is going to be what? It is going to be n plus 1 by 2 of pi. So pi by 2, 3 pi by 2, 5 pi by 2, n plus 1 by 2 into pi. So for every n plus 1 by 2 of pi, this is going to be equal to 0. So this is going to give us the expression how omega n will be equal to what? N plus 1 by 2 like this, n plus 1 by 2 into pi under root of g by rho by L. This is going to be the expression for what? Natural frequency omega n. I hope this is clear. Okay, so this is how we get. The only thing is that to find out the natural frequency, we just need the solution form and we need to apply what? The boundary condition. Like here we apply the boundary condition for torque and then we apply the boundary condition for the rotation at the fixed end. Okay. This is what we have been doing since question number 1, right? As you can see over here in question number 1 also what we did was we applied the boundary condition for the del u by del x, right? Del u by del x we applied the boundary condition. For this question number 2 also we applied the boundary condition at x is equals to 0, u is going to be equal to del u by del x is going to be 0. Then for this also what we did, we applied the concept of boundary condition. What did we do? X was going to be equal to 0, so we apply the boundary condition that del theta by del x is going to be what? Equal to 0. Because that is, see, we are using del theta by del x. Why? Because we are evaluating theta with respect to every x, since it's a partial differential equation, right? We are not saying that theta is uh, indifferent from the value of x. It's changing with respect to x only. So what we are doing is we are talking about the slope. with respect to x, not with respect to time, but with respect to x, the rate of change of theta with respect to the rate of change of x. Okay. Now coming on to question number 4. So we have a drill pipe of an oil well that terminates at the lower end in a rod containing a cutting bit. Derive the expression for the natural frequencies, assuming that the drill pipe to be a uniform and fixed at the upper end of the rod and cutter to be represented by an end mass of moment of inertia J naught. So this is a system, right? We are having a pipe and then we have a cutter in the down. Then we have a pipe which is of a certain length, right? And at the cutter, we are assuming it as nothing but a end mass with a moment of inertia J naught. Then we are talking about the moment of inertia, and the cutter is also going to work when it rotates. So we are basically talking about the torsional motion, rotational motion. So okay, let's just solve it. So firstly, talking about how the system is going to be, right? So see again, as we did in the question where we had a mass which was suspended at the end of the bar, there was the contribution of the inertia force, correct? There was the contribution of the inertia force. Now over here also we have the inertia of the cutter which we need to consider in order to find out how the system is behaving. So firstly, if we talk about the end part of the system, so we have like over here where we have the cutter, the cutter like this. This is not looking very good. There's the cutter, something like this. Right. Now, if you look over here, that's with the cutter, what is actually happening, right? So this cutter is going to have a torque over here, right? We are just considering the upper part. There is going to be a this part also, right? We are just considering the lower part of it. So it is going to have a torque. Why? Because this is going to have a torque, right? Now this torque is there, and this is being balanced by what? This is being balanced by the movement theta, which induces the inertial moment, okay, which is minus J naught del square theta by del t square. At what? At x is equals to n. Not for every L, but specifically at x is equals to L. See clearly the second differential of theta with respect to time at what? At x is equals to L. Because the second differential of theta with respect to time is varying with x. That is what we are talking about, a continuous system. With x, it varies. So we are specifically talking about at the position L, and we are considering at this tau as a very small distance from the cutter. Okay, just for the force balance or moment balance to be precise. Again, what is going to be the solution? Same, A sine of omega rho by g x, B cos omega rho by g x, this whole into C sine of omega t into d cos of omega t. This is the solution. Again, we know that at the fixed end, what is going to happen? At the fixed end, theta is going to be 0. So at the fixed end, we are going to have del theta by del x going to be equal to what? 0 at x is equals to 0, right? Which is going to give us b is equal to 0 because it is present with the cos expression. Sorry. Okay. Apart from that, what are we going to get? Okay, this is known to us, so we will not be writing it again and again. We'll just write b is equal to 0. Coming on to further things. See, what is this? How can we write this torque value? We need to find out how the torque is related, right? Then only we can write the expression for the torque balance. Till now, we don't know. So if you remember that for a rod where we are subjecting it to some kind of a tension, we can write the angle of twist as what? D theta as what? T into dx divided by IP into G. T into dx divided by IP into G. This is what the angle of twist. T is what? Tension. IP is what? Polar moment of inertia. Okay. And then we have G as what? Shear modulus. Shear modulus. So this is what we are going to get. So then we can get T of L as what? Or just write this as T of L. IP into G into d theta by dx. Now I have the expression, so I can equate it to the what? Inertia, right? So what is it going to give us? By moment, valence comma. What are we going to get? G IP d theta by dx at x is equals to L is going to be equal to what? J theta omega square theta of x is equal to theta at x is equals to x. Okay. Yeah, perfect. Okay. So if we put the solution that we obtained over here, where we have already found the assumptions, putting the solution, what do we get? Right? If you put this solution. Now, since your just a second. Yes, we have d theta by dx, so we need to find out the expression for like we need to differentiate it, but we'll not be getting into this. You can just see and check how is it going to get differentiated, because we need to differentiate theta with respect to x. So the multiplication of c sine of omega t and cos of omega t, it will remain for both the cases, and you will see that it will cancel out as well, because the differentiation is just with respect to, as you can see, in both the cases differentiation is with respect to what? Okay, I hope you understand why we have written it as omega square into theta, right? Because theta was like in terms of what? Theta was in terms of cos omega t sin omega t. So if you differentiate it, we are just going to get the expression as same, but with a minus. It's expression of theta only, but with a minus. So basically theta double dot, or sorry, I should not write it as theta double dot. Del square theta by del t square is going to be nothing but minus of omega square into theta. That you can check also. That is why we have replaced it like this, and the minus sign is also vanished. Okay. So if you look over here, we will get c sin of omega t and plus d c cos of omega t plus d sin of omega t. Anyways, whatever it is, it will get cancelled out. Okay, in both the cases. So we have just the expression for x. Okay, so we just need to differentiate it and then put into it. So we differentiate it, what are we going to get? Firstly, we are going to have a sine component and then we are going to have a cos component. Okay, since we have already found out that at the fixed end theta is 0, so b is going to be equal to 0. Then only it is possible because a sine omega t will go to 0 because of sine of 0. So b term will already go, only the component for the a part will remain, and a also is going to appear on both the sides, so it will also get cancelled. So what are we going to get finally is g into ip omega under root of rho by g cos of omega rho by g l is equal to j naught omega square sine of omega under root rho by g into l. Again, we are going to get an expression for the tan, right? So tan of omega l under root rho by g is going to be equal to what? Ip by omega j naught into rho into g. Okay, so this is going to give us Ip rho L by omega j naught into L into under root of G by rho. Now, if you look over here, Ip into rho into L is what? Ip into rho into L is what? It is the J of rod, right? It is the J of rod. Ip was what? It was the polar moment of inertia, right? It was the polar moment of inertia. The polar moment of inertia, when it is multiplied by rho into L, what is it going to give us? It is going to give us J of rod, right? So this will be nothing but J of rod divided by J naught omega L under root of G by rho, right? So what do we get? We get again, if you look closely, we have this expression. We send omega L and this part on the left hand side. Again, we are going to get beta is equal to, or beta into tan beta is equal to what? J of rod by J naught, where beta is omega L under root of rho by G. Okay, I hope this is clear. Okay, so what do we get? We get beta into tan of beta in terms of J of rod by J naught, and then we have beta, which we have assumed like this. So this is it for the question. It asked us to basically find out the natural frequency expression, and we found out. Again, we just assumed a solution. We used the boundary conditions. We got an expression by equating the inertia moment and the moment which is present in the rod at the end L, definitely. From where we got an expression, and from there we can find out the natural frequency. But then again, whatever the frequencies that we are finding out, these are the fundamental frequencies, because for the continuous system, they are going to be infinite frequencies. And you must have learned in the lectures that the fundamental, all the other frequencies are the integral multiples of what? The fundamental frequencies, right? So if we know the fundamental frequency, we can find out the other frequencies. And I would suggest you to just go and search on Google or maybe on YouTube to look into the Chandley patterns. So basically, we have this, they do this experiment where they have a plate and then they start oscillating the plate using a exciter at different frequencies. Firstly, the fundamental frequency and then the integral multiples of fundamental frequencies. And then you can see that there are different patterns that can be seen by the sand that is present on the plate. Okay, so, and those patterns are going to show the mode shapes of the system. So basically those patterns are because of the nodes that are present on the plate. Okay. So if you put sand on it and then you start vibrating the plate, the nodes are going to be stationary with respect to time. So the stand is going to be remaining on only the nodes and then you can see the shape of the node. Okay. So maybe you can see it. It is a very interesting experiment. Anyways, we need to determine the first two natural frequencies for a drill pipe of 5,000-meter long, or the values of this and this. Okay, so this is basically related to the previous question. In the previous question, we derived the expression, right? Now, in this question, we need to use that expression to find out the values of the first two natural frequencies. And the same thing that I told you that it is usually the integral multiple. I'll tell you that. Just a second. Okay, so in the previous question, what was the expression that we got? This one. We had beta into tan of beta is equal to what? J of rod by J naught. Right? This was a expression for natural frequency. Okay. Now, this is the expression which is fine. But again, this is a transcendental equation. So we need to solve it simultaneously. See, there are two things. Either we assume again that beta is very small, but that is not true always, right? That is an assumption. That is not always going to be true. That every time we are assuming tan of beta is beta, because now we are working on a continuous system. See, in the previous question, what we did was we found this kind of equation and then we used assumption and then we saw that okay, the natural frequency expression that we got, it was same as if I have considered my system as a single degree of freedom system where the rod was not having any mass. But here we are not actually working on that assumption. We are considering the system as a continuous system. So for a continuous system, always taking the assumption is not true. Okay, it's not right, because we can take the assumption, but only for the case when a system is being used for a practical application where it can be assumed to be very small and the assumptions are actually true, but that is not always true for the continuous system. So if we want to model it as a continuous system, we need to solve this transcendental equation. Now, we don't know how to solve it, okay? A transcendental equation. So if it would have been an algebraic equation of some order 2 or 3, we could have solved it because we know the technique. Okay, but for this case, we don't know. So what do we do is we use some kind of a books that have given that how do we solve such kind of a transcendental equation. Okay, so they give us the value, right? They give us the value which we can use in order to get the solution. Okay, so basically we get the values of beta, right? So what is going to be the values of beta for which this is going to be equal to this. So in this question, we have J rod and J naught. So this expression is going to become beta into tan of beta is going to be what? 71.4 divided by 29.3. So this is going to be around 2.44. Now we can use any kind of a book that talks about how to find out the roots of the transcendental equation. Basically, there are many books that you can refer to, and from there you are going to get that for a system of this type, what are the possible solutions? Now, if you remember, beta is definitely tan beta is of a repetitive nature. So we are going to get multiple numbers of values of beta that is going to satisfy the solution. So I have taken the reference and then it was written that beta could be equal to 1.135 or it could be 3.722 and likewise. Okay, so we can use it. So now I know the values of beta. It depends upon J naught by J naught. I just have to substitute it in order to get the omega n. Remember, beta was nothing but omega L under root rho by G, right? Omega I need to find out. L is what? 5000. And rho by G is going to have a particular value. It will depend upon the density of the material and the shear modulus of the material. So for now, I have just evaluated it and we can write it as 9.4 into 10 to the power minus 5. This will definitely depend upon material to material since it's a material property. Okay, and this is equal to what? 1.135. This will give us the value of omega n as 2.41 radians per second. Omega n 1. Likewise, omega n2 is going to be what? Omega n into 5000 into 9.4 into 10 to the power minus 5 is going to be equal to what? 7.93. This will give us, sorry, not 7.93, 3.722. This is going to give us what? Omega n2 as 7.93 radians per second. So these are the first two natural frequencies, and you can see that they are almost related by the integral values, right? Because if I do 7.93 by 2.41, let us check how much it comes. It is 7.93 divided by 2.41, around 3.2. So if I'm saying that it is the integral multiple doesn't mean that it's the exact multiple. It could be somewhat related 3.2, 2.9, something of that type. Okay. Now coming on to the next question. We have a turbine blade is modeled as a uniform cantilever beam. Okay. The blade is 0.3 meter long with constant cross-section area of 100 square millimeter, material density of 7000 kg per meter, and the flexure rigidity of EI is equals to 50 Newton meter square. For fundamental mode, the value of constant beta into L is 1.875. For the second mode, the value of the constant beta L is 4.694. The difference between the second and the fundamental natural frequency of the beam in radian per second. So basically, we are modeling a turbine blade which is considered as a cantilever beam. Like this, we have a cantilever beam where the blade is what? 0.3 meter in length. And the area is what? Definitely it is the cross-sectional area. Material density rho, it should be cube, kg per meter cube. Okay. And we have the values of EI, 15 Newton meter square. Okay, and then we have the values of beta L for the first mode and the second mode. Anyways, where is this value coming from? So if you remember that for a cantilever beam, there we get the expression, right? We have the expression such that omega n square is nothing but beta n square under root E I by rho A. there was this expression, as far as I remember, sine beta L plus cos beta L is equal to 1 or plus 1 is equal to 0. I don't know. There was some expression like this only, which was being used. And from this expression only, by solving it, we get the, was it plus or was it multiplication? I guess it was multiplication, maybe. Okay, I'm not so sure about this. Maybe you can just check. I don't remember the expression correctly. But from this expression only, we were again solving it, and then we got the expression for beta L, that omega n square is written in terms of beta L, where beta L we have to take out from the expression only. So beta L values we know. Now we have beta into L values, but here we have to use the beta, right? So what we can do is, with this expression, I can multiply with L square and divide by L square into L square by L square. Okay, so this is going to give us L into beta n square EI by rho A L to the power 4. Correct. Now, EI, we already know the value. Rho, we know the value. But I think that for this expression, rho was essentially the mass density per unit length. It was not with respect to the volume. So we need to find out that expression. You can just write it as mu for now. Okay, so EI value we already know. Mu is what? Okay, rho is fine, I guess. We just need to find out rho into A. It is going to give us mu only, right? So for the first frequency, which is omega n square, so we have beta into L for the first case, which is 1.8745 square into E into I, which is 15, divided by rho into A. A is in mm square, so this is going to be mm is 10 to the power minus 3, 10 to the power minus 3, 10 to the power 2, 10 to the power minus 4 meter square into 7,000, which is 0.7 into 0.3 to the power 4. Okay, so this is going to give the value of omega 1 as nothing but, okay, there's no square over here, it is omega 1 only, and omega 1 is given as 180.82 radians per second. Okay, 180.82 radians per second. This is the first frequency, definitely. Apart from that, we are going to have a second frequency, which will depend upon the other value of beta. So, which is going to be omega n2 is going to be what value? 4.694 square into under root of 15 divided by 0.7 into again 0.3 to the power 4. When we solve it, this is not square, okay? This is basically 2. This is not square. This is the second natural frequency actually. This is what this will turn out to be 1133.29 radians per second. This is the second natural frequency. Okay. And we need to find out the difference. Difference, okay, difference between the first and second natural frequencies, which is omega n2 minus omega n1. This is nothing but 1133.29 minus 180.82, which will be 952.46 radians per second. So this is the answer to the problem. I hope this is clear. Coming on to the other question. So we have a stretched string of length 1.2 meter with a linear mass density of 0.005 kg per meter, which is fixed at both the ends and kept under a tension of 80 Newton. Determine the fundamental natural frequency. We have to determine the angular frequency of the second mode and find the difference between the second and the first natural frequency. It is similar to the previous question. The only difference is that the previous question was about a cantilever beam and this question is about a string. Okay. So if you remember, for a string, what was happening was we have basically a string, a thin string, which is fixed from both the end after a 80 Newton of tension is applied on it. Okay. So we have basically length is 1.2 meter, linear mass density, which we can write as mu, which is 0.005 kg per meter. Okay. Then we have L, which is okay, L, we have already taken the length. Apart from that, what do we have? T, which is the tension in the string, which is 80 Newton. All right. And we assume N as the node number. Basically, N is related because you know that for a string, we have the frequencies as a integral multiple. So N is required in order to define the fundamental frequency, then the second modes, third mode, and likewise. Okay. Now, for a string, the expression of omega n is given as what? N pi into under root of T by mu L square, where we know what N, capital T, mu, and capital L are. We just need to put up the values and find out what omega n. Correct? Okay. Now, for this, if we need to find out, firstly, what you need to understand is that omega, it will be dependent upon the value of n. And the difference in the first mode, second mode, third mode, and fourth mode is just the value of n. Everything else in this expression is going to be same, right? So what is happening is that omega 1 is what? Pi into under root T by mu L square. Omega 2 is what? 2 pi under root T by mu L square. Omega 3 is what? T by mu L square. It should be 3 over L. Okay, this is the case. We need to put on the values. So if we just evaluate pi into this everything, we are just going to get the values. At least we can just, if we evaluate the under root of whatever the terms is, we are going to get the value by simply multiplying with pi to pi and everything, right? So we'll just first evaluate that under root of T by mu L square. The tension is 80 divided by mu 0.005, and then L is how much? 1.2 under root. So this will turn out to be, I've already written the value, 80 divided by 0.0072 under root. This will give us under root of 1111.11, something like this. It's going to be 5 months, and this will turn out to be 105.409. Okay, so talking about the first omega 1, it's going to be pi into 105.49. This will turn out to be 331.1529 radians per second. This is the first natural frequency, which is the first mode also. When we talk about the second one, we have seen from here that omega 2 by omega 1 is what? 2. So omega 2 is nothing but twice of omega 1. Omega 3 is what? Twice of omega 1. And likewise, omega n is what? N times of omega 1. This is true for the different modes. Okay, so here we say that omega 1 is the fundamental mode, and omega 2 is what? It is the second mode. Okay, it is the second fundamental mode, you can say. Okay, so we just need to put omega 2 as 2 into omega 1, which will be nothing but 662.305884 radians per second. Okay. And then we are supposed to find the difference. However, there's nothing to find the difference because delta of omega is omega 2 minus omega 1, which is nothing but twice of omega 1 minus omega 1. So the difference is nothing but omega 1, which is 331.1529. And if we talk about the nth difference between n omega, so it will be omega n minus omega 1, which is nothing but n omega 1 minus omega 1. This is going to be n minus 1 omega 1 is going to be the difference, and we can just use this expression, it's a general expression, in order to find out the difference between the nth mode and the fundamental mode, which is omega 1. What is interesting over here is to see that it is the exact integral multiple, right? For the fundamental mode or the first mode, the second mode is nothing but the twice of the fundamental mode. Okay, so it is easy then, to evaluate, and in order to understand also that in the physical case also, that if I find out one fundamental mode for a string which is in a physical condition, I know how much uh, other it is going to vibrate at some other kind of a frequency, right? That is how the guitar string works, right? I hope that you people know that for a guitar there are various strings, okay? And for those strings, the tension is different in every string. And so for if you have some knowledge about how a guitar is used, so basically there are 5 to 6 different strings, and then there is a different kind of a tension in every string. And what you're supposed to do is you're supposed to give some actuation from your thumb to the guitar, and it is done at different places in order to produce different sound, right? So what is happening is that when I am giving some perturbation at some different places, okay, if I'm giving perturbation at different places, it is going to create different modes, and those modes are going to give different kind of a noise. And that is how a guitar works, and that is how it is able to produce so many kind of a noise, because for different tensions we can have infinite number of modes, and corresponding to those infinite number of modes we can have different kind of noises. However, it is not taught for infinite types. There are only n, let us say some n number of finite sounds that can be taken out from a particular wire of some particular tension and particular dimension. Okay, because it will depend upon that also. It will depend upon the dimension, how much the diameter is, how much the weight is, like the mass per unit length also. It also matters. So depending upon that, different at the perturbation at different places is going to produce different kind of a sound, because it is actuating or it is giving some impact to the system at different modes. How modes? So if you look, how the mode shape actually changes is that the mode shape in general is given for a string as phi n of x as given as sine of n pi x by L. Okay. So phi 1 of x is what? Sine of pi x by L. Phi 2 of x is what? Sine of 2 pi x by L. So if I want to plot phi 1 with x, how is it going to be? I have a fixed side. This is the initial state. These are the two fixed sides. Sine of pi x by L. X is varying from 0 to L. At x is equals to 0, we have sine of 0. So it is going to be 0. At x is equals to L, sine of, we are going to get sine of pi, which is going to be 0. So the graph is going to be something like sine of x, like this. This is the first mode. So if for a guitar, or just for a string, if I have a string which is fixed from two ends, and I just take the midpoint and perturb it in the upward or downward direction, it is going to create the first mode of oscillation. Why first mode? Why first mode? Because I have given the perturbation so that the first mode is actuating. Because the perturbation that is given, it is near to the first mode, and that is why it is going to get activated like this. Now for the second mode, if I see, it is sine of 2 pi x by L. So it is something like sine of x from 0 to 2 pi. So we have something like this, and this, like this. Okay, this is what? This is the second mode. Here if we have a deflection of 1, here I have a deflection of 1, and this is -1. Okay, so if I actuate near to 1 by 4th of the string in the upward or downward direction, it will, since it is near to the second mode is going to get actuated. It is going to show the vibration like that of the second mode, and that is why it is going to produce different kind of sound for different kind of for different places at which the perturbation is going to take place. I hope it is clear. Now we'll come on to question number 8. Here we have to determine the wave velocity along a rope whose mass is 0.371 kg per meter when it is stretched by 444 Newton tension. Okay. So C, basically for a rope, we define the wave velocity. Wave velocity V as nothing but under root of P by mu, where T is what? Tension in the rope. And mu is what? It is a mass per unit length. So for this question, we already have the mass per unit length and we already know the tension. So we just need to put the values 444 divided by 0.371, which will give us 34.55 meter per second. This is the wave velocity. Okay. So this question was just a simple question, just a numeric value you need to find out. That's it. Coming on to question number 9. This is something related to the guitar string. We have a guitar string of length 0.8 meter and has a mass per unit length of 0.005 kg per meter. Initially, the string is under a tension of 80 Newton. Find its fundamental frequency. If the tension is increased to 320 Newton, what will be the new fundamental frequency? Comment on how the frequency changes with tension. So this is again something which is related to the concept of guitars. As I told you that for a guitar, for making different sound from the strings, either there is a difference in tension, okay, on those strings, and there is difference in where you actuate or give perturbation to the system or the string, right? Like for a string, there are various strings, okay? Like for example, if I have a guitar, something like this, something like this, okay? There are various strings, and then there are kind of something like nut where for which you can just rotate it and the string will get taut. Okay, and these are the strings. So maybe these strings can have a tension of T1, T2, and then T3. Depending upon these tensions, it is going to produce different sound, and depending upon whether I strike it over here, over here, over here, over here, over here, it is going to produce different sound because different kind of mode is going to be actuated, right? As I told you, when we give some perturbation to the system, if that whatever perturbation I am giving, the perturbation near whichever it is near to, okay, like let us say that a perturbation is near to some frequency fund some modal frequency, let us say n, then the nth modal frequency will work. Like for the nth modal frequency, I'm going to have nth mode, yeah, or the nth eigenfrequency, eigenvalue, sorry, eigendirection. So for that eigendirection or eigenvector, if I'm going to give a perturbation which is near to that eigenvector, a perturbation which is near to that mode shape, okay, it will excite that particular mode only. Okay, so if the perturbation is near to the ith mode shape, it is going to excite the ith mode, the ith frequency. Likewise, if there is some nth mode shape, and if I'm going a perturbation which is near to the nth mode shape, then the nth natural modal frequency is going to get excited. Okay, and it is going to produce that kind of a vibration. Because of that, it is going to produce that kind of acoustic sound. Okay, so again, from this question, what it is this question is trying to do is it is going to make the idea clear of how different kind of a tension is going to affect the frequency. Okay, so we have a guitar string. It has a length of 0.8 meter. We have a tension of T1 of 80 Newton, and then it was changed to T2, which was 320 Newton. Okay, then we have mu as 0.005 kg per meter. Okay, and yeah, these are the things that we have. So if you remember that we had an expression in the previous question for the wave velocity. How are we going to use the wave velocity? So the wave velocity was under root of t by mu. Okay, and then the frequency is given as wave velocity by 2 times of L, which is nothing but 1 by 2L under root of t by mu. Okay, maybe I should write length of string tension in the string mass per unit length. Okay, and v is nothing but it is the wave velocity. F is the frequency in hertz. So then we can find the frequencies corresponding to the different tension. So for the first case, when we have T1 as 80, we have the frequency as 1 by 2 into 0.8 into under root of T, which is what? 320 divided by 0.005. This is going to give us a value of 79.057 hertz. This is F1. Okay. For F2, second case, we have T2 as 320 Newton. So we have F2 as 1 by 2L under root of T by mu, which is nothing but 1 by 2 into 0.08. No, it is 0.8 only. Into 320 divided by what? Mu, which is 0.005. This will give a value of, see, you can just write it as, because T2 is nothing but, if you look over here, T2 is what? It is 4 times of T1, right? It is an integral multiple of T1. So we can write it as 1 by twice of L under root of 4 times of T1 by mu, which is nothing but 2 into 1 by 2L under root of T1 by mu, where we have already evaluated the value of that, 79.057. 2 into 79.057 hertz, which will turn out to be around 158.11388 hertz. This is F2, right? This is what? F2. The last part of the question says that comment on how frequency changes with tension. So as it is evident over here that the frequency is nothing but directly proportional to under root of tension. Under root of tension, right? So if my tension increases, the frequency increases, but with the under root, right? But with a under root. Okay. So it's like if I try to create a plot, how are we going to get f is equals to some c into under root of t, or we have f square by c square is what? T. So when we try to plot y is equals to x square, how do we get it? We get it like this. Okay. And when we plot x is equals to y square, how is the plot? Something like this. That is what we have over here, right? That is what we have over here. We have T tension as what? F square, right? So this is for what? This is x is equals to y square, but maybe y tension is our input, right? So this is x square. Okay, yeah, this is fine. This is the graph of y is equals to x square. But we need y x is equals to y square. Yeah, this is for x is equals to y square. Okay, but we want it to be f square. Like I want tension in terms of f square. Okay, so how are we going to plot? We want tension in the y-axis and f in the x-axis. Sorry, tension. This is going to be what? Like this, right? Positive side because frequency cannot be negative, definitely. Okay, so as the tension increases, what is going to happen? The frequency is going to increase, but it is not going to increase linearly. It is going to increase with a square function. So it will be something like this, okay, like a parabola kind of thing. And this is how it is going to change. So basically, if I want to increase the tension, increase the frequency of my spring, I would introduce a tension like that. Now, these are the fundamental frequencies, right? So how can we control, how do we even want to control the fundamental frequencies? So the thing is that if let us say that I want to oscillate it at lower frequencies, okay, and I want the second or third fundamental frequency to be less than 10 hertz, then what will I do? I will try to give a tension such that my first three frequencies come under 100 hertz. But now I want a case where I want all my frequencies to lie above 200 hertz. So then I will give the tension to the string in such a way that even the fundamental frequency is going to be either 200 hertz or maybe greater than that. I have the expression for it. I can decide the length and I can decide the tension, mass density. It's not always in my hand. Like if I just have a one sample of a string and then I just want you to use that one sample only in order to produce different kind of a noise or in order to produce different kind of a mode shape or different kind of a length, then I can just use these calculations in order to find that out. Right? I hope that this is clear. Okay. So this week's live session was mostly about when we were talking about continuous system, we have clearly seen that how the effect of a linear system as compared to a sorry, not linear actually, one degree of freedom system as compared to a continuous system can be done. Okay, we have already seen that From the equation of a continuous system, we can directly get whatever we were getting after using the 1 degree of freedom system. And it is also important to note that solving a continuous system is difficult because it's a partial differential equation, right? And solving a partial differential equation is difficult as compared to solving a linear ordinary differential equation. So definitely solving this is difficult, but then if we require a system, we require a practical application wherein a precision and accuracy is required, and we do not want any kind of a catastrophic failure, and we do not want any kind of a assumption of approximation of how the system is going to behave. It is important that we use the formulations of a continuous system and model it as a partial differential equation and solve it. However, there are now very high computational techniques wherein we can just use our model, I mean the making the 3D diagram of our model and just giving it to ANSYS or COMSOL kind of a software, and just do the simulation work in order to get how the system is going to behave. So basically we make the 3D model and we apply whatever the forces are there in the system. We make the references or whatever the frame is fixed, we make it like that, and then we apply the force, and then we do the simulation that we want to do, right? And once we do the simulation, we know how the system is going to behave. But then in those softwares also, we use meshing techniques. So every model, 3D model, is made into small parts, and those small parts are then solved using the concepts of solving the partial differential equation using some numerical techniques. And the smaller the part gets, the more the accuracy is, but then the more is the computational cost. So there is always optimization between what should be the computational cost or the time of computation and the accuracy that we want for our system. Okay, so it is easier definitely instead of solving mathematical problems, but then for some systems it is important that we solve the mathematical problem because then it gives us a closed form solution which is much more reliable than the numerical solution, right? Numerical solution can have some kind of error which may get propagated as we integrate the system, and it is going to show us a behavior that we don't even know, right? Like for example, if I have a random system which I don't know how it is going to behave, and I just apply the simulation and it is going to give me some behavior that I may just accept, but which is not practically possible, right? That is why it is essential that after we make a simulation model, we basically see its practical validation, or we make a practical model, like a analytical model, and then we can use the simulation technique and compare it with the analytical model. Likewise also we can actually validate our simulated response, right? So okay, that is it for the today's live session, and tomorrow we are having a extra session at 11 a.m. I hope that you people, I think because you people are not able to attend since of the timing of the lecture, but I hope that you will come tomorrow 11 a.m. so that we can discuss about what we did in the course. Okay. Okay, then we'll meet for the last time tomorrow at 11 a.m. Thank you so much for your time. I'm ending the live session now.